Okay, so we are going to go over one sampled. Uh, we're going to go over one sample tests of hypotheses. So essentially what we're doing here is we have a population and we want to determine whether or not this population, we're going to take a sample from this population and we're going to determine if this sample is the same, if this sample is different, if, what is the relation of this sample to the population. And so we have a hypothesis. Sometimes you're going to see here, you're going to see mu is greater than 60,000 or greater than or equal to 60,000. Mu is less than or equal to 60,000, or you'll see x bar is greater than. Basically what this is saying is the new sample that you're taking, the new population estimate, the new point estimate, if you will, is greater than or equal to 60,000. And when we are testing null hypotheses, that is exactly what we're doing. We are testing the null hypotheses, and so we either do not reject the null hypotheses or we reject the null hypotheses. So right here we have one-tailed and two-tailed tests. The very first one, we've got a one-tailed test, and you notice the alternative hypothesis says that 60,000 miles, that mu or x bar or whatever it is that we're testing is less than 60,000. So 60,000 really is right here, right in the middle. And then the arrow points to whichever direction the critical value is going to go. And that's really important. So when you see this here, the alternative hypotheses, if it's a one-tailed test, the alternative hypotheses arrow will point to the less than side will always be the critical value, okay? So here we've got a left-tailed test with an alpha of 0.05, and notice that the alpha of 0.05, right here we've got negative 1.645. That right there means that the alpha is all loaded on one side. Okay, so the probability of being more extreme than negative 1.645 is 5% or 0.05 probability. Okay, here we've got a two-tailed test, and the reason why we know that is it does not indicate a direction. The null hypothesis is that mu, or the new sample, is equal to 65,000 per year. The alternative hypothesis is that the new sample is not equal to 65,000 per year with an alpha of 0.05. And so you see here something similar to the 95% confidence interval with critical values at negative 1.96 and 1.96. And so you've got an alpha, or you've got the probability of being above 1.96. The probability of being above 1.96 is 0.025, or 2.5%, and the probability of being below negative 1.96 is 0.025, or 2.5%. And if you add 2.5, or if you add 0.025 plus 0.025, that gives you your alpha of 0.05. And then this one right here, we've got a right-tailed test with an alpha of 0.05, and once again we can tell that it's a right-tailed test, that the critical value is in the right tail because of the direction of the alternative hypotheses. Okay, and so we can tell right here 453 grams is where the 0 is, or the mu, and then what we're testing, the new value, the alternative hypotheses is that the new value is greater than 453 grams with a critical value of 1.645, which means that the probability of it being greater than 1.645 is 0.05 or 5%. Okay, here's I'm not going to read through all of this. You can take that if you want. But what we're doing here is we're calculating the z-value. We've got the population, the previous population, and let me see right up here. I guess I will read through a little bit of this. Let me get the pen. So right here we've got a normal distribution. Oh, I'm going to pause this. Sorry, my pen wasn't working properly. So we've got a normal distribution with a mean of 200, okay, and a standard deviation of 16. That's the original population data. And so you see the mu, and then you see the standard deviation of the original population. New production methods have been introduced, and the Vice President Manufacturing would like to investigate. Is there a mean number of desks produced different from 200 at the new production methods have been introduced, and the Vice President of Manufacturing would like to investigate whether or not there has been a change in weekly production of the model. Is the mean number of desks produced different from 200 at the 0.01 significant level? Okay, so right there, we're going to determine whether or not that z value is more extreme than an alpha of 0.01, okay, or the z value at an alpha of 0.01, okay. So we have the hypothesis, or the null hypothesis right here. The null hypothesis is that mu is equal to 200 desks. The null hypothesis, or sorry, the alternative hypothesis is that mu is not equal. And when we see mu, what we're talking about is this is the new population, the new sample, okay? And we were using the new sample as a point estimate for we're using the new sample as a point estimate to adjust the new population, okay? So right here you see negative 2.56 and 2.56 because this is a two-tailed test. I don't know. Okay. This is a two-tailed test. Excuse me. You've got 0.005 right here, and you've got 0.005 right here. So the probability of it being at this critical value or beyond, or more extreme, is 0.005, and the probability of it being at this critical value or beyond is 0.005. And so if it is, if the z value that you calculate in the previous slide, if the z value that you calculate, the new z value, is more extreme than either of these two critical points, you reject the null hypothesis. But if it's less extreme than these 2 points, then you fail to reject the null hypothesis. So let's keep on moving. So the mean number of desks produced last year, 50 weeks because the plant was shut down for 2 weeks, is 203.5. The standard deviation of the population is 16 desks. Compute Z with formula T. Okay, so we've got, from the previous information, we've got 216. And so the standard deviation is 16. So right here we've got 203, which is the new sample mean, and then we have the previous population mean. So you've got the new sample mean minus the previous population mean divided by the standard deviation divided by the square root of the number in the sample, which gives us a z value of 1.547. So that puts us at 1.547, which is about there. So the question is 1.547 more extreme than this critical value or less extreme than this critical value? And the answer is it is less extreme than that critical value, and because it's less extreme than that critical value, we do not reject the null hypothesis, or we fail to reject the null hypothesis, and we conclude that they're not different. That the new production methods do not actually, cause, a significant difference. Okay. So suppose instead of wanting to know if there has been a change in the mean number of desks assembled, the Vice President wants to know if there had been an increase in the number of units assembled. Okay, so can we conclude because of the improved production method that the mean number of desks assembled last week, 50, in the last 50 weeks was more than 200 with using an alpha of 0.01. Now notice the alpha of 0.01 split between two tails, and the alpha of 0.01 all loaded on one tail. Okay, so the critical value for an alpha of 0.01 on one tail is 2.326. The alpha on two tails is 2.576 and negative 2.576 because there's 0.005, half of the alpha is on one side, half of the alpha is on the other side. Also, this is a directional hypothesis, which means it's a one-tailed test. This is a non-directional hypothesis. And notice, once again, with the alternative hypothesis, it's pointing in the direction of the critical value. So, can we conclude that it is significant? Okay, because the improved production method, that the mean number of desks assembled in the last week, so once again, it's still 1.547, so it's still right here, so it's still less than the critical value, so even making it a one-tailed test doesn't do anything for it. It's still not critical. Okay, it still does not go past the critical value. So that's the difference between one-tailed and two-tailed, and we'll move on to the next lecture.